All right. Hopefully, assuming I can fix this, this is starting as, yeah, anyway, we're going to graph one more function. This is the last function that we're going to graph. This one's really hard. I started this at the end of the other video, but I just made like one mistake, which was really annoying. So I'm just doing it over again. So here it is. So the function is f of x equals negative x to the 2/3, x minus 6 to the 1/3. We would like to learn every single thing there is to know about this function. Okay, let's go. And again, please try this yourself. Pause it right now, take the derivative, factor the derivative, and then catch back up with me, because I'm going to go fast, or fast-ish. Try not to make any mistakes. All right, let's differentiate. I need to use the product rule. So product rule says derivative of the first, so that's negative 2/3 x to the negative 1/3 the first times the second, x minus 6 to the 1/3, plus the first, so negative x to the 2/3, times the derivative of the second. And the derivative of this is going to be 1/3 x minus 6 to the negative 2/3. Back inside, derivative is 1. Okay, so I get this kind of disgusting mess, but we will now do some algebra. Let's see, they both have a negative, so I can take out a negative. They also both have a 1/3, so I'll take out a third. I need to take out some number of x's. Let's take out x to the negative 1/3, because that's the lower of the two. And they both have some x minus 6's. Let's take out x minus 6 to the negative 2/3, because again, that's the smallest. If I do that, I'm left with, I got the negative, I got the 3, I got the x, so I'm left with a 2 and some number of x minus 6's, which happens to be one of them. Took out the minus, took out the 1/3. This needs to be, I need to put an x here because, and then I grabbed that already. So it's just this. So actually, this is not so bad at all. This derivative is just negative 1/3 x to the negative 1/3 x minus 6 times 3, do something wrong? 2, just 3x minus 6, right? Yeah. No, 3x minus 12. Yeah, 3x minus 12. 2x and 3x minus 12. 3x minus 12. Okay, so the 3 cancels, so that's even nicer. So it's just negative x to the, well, let's just make it pretty. If the 3 is gone, then, well, okay. So I get negative x to the negative 1/3 times x minus 6 times that 3 makes this an x minus 4. So this is a very nice form to, this is to the negative 2/3, and that's to the negative 2/3. So, yeah. So that means that if you actually write this out with no negative exponents, it becomes negative x minus 4 over cube root x minus 6 to the 2/3. And I think that's right. Hope that's right. Yeah. That is the first derivative. And however, this is the form which I think is easiest to differentiate. So let's jump right in and take the derivative of that. It's actually really useful right now to have something which is called the triple product rule. I don't think we ever did this. We're just gonna do this. We're just gonna do this really fast. So just flip this crap over. Let's zoom in to the backboard. I know it's all blurry. So let's suppose that I'm trying to take the derivative of the product of three functions. So f of x, g of x, h of x. How do I do this? Well, there's like a happy little formula for this. Essentially, I just treat two of them as like one. So, okay, product rule says that this is going to be the derivative of the first times the second plus the first, so f of x, g of x, times the derivative of the second. But then, of course, this requires the product rule, so that's f prime g plus g prime f. And then all of that is times h of x. And then I still have this plus f of x, g of x times h prime of x. And if you multiply this out, you get a nice formula which says that it's the derivative of the first times the other two plus the derivative of the middle one times the other two plus the derivative of the last one times the other two. So I don't know. I call that the triple product rule. It's just a nice little thing to know, and I think it's a homework problem. It's a homework problem in our textbook, but I don't know if I signed it this year. I certainly don't remember going over it. Okay, so back to the front board, and basically, I think the triple product rule is really useful in this case right here, because I want to find the second derivative now. All right, so what is f double prime of x? Well, let's just freaking jump right in. So it's going to be the derivative of the first one. Yeah. So the negative 1/3 comes down, so it's 1/3 x to the negative 4/3. Yeah, do it first. Times the other two. So x minus 6 to the negative 2/3 x minus 4. Yeah, for the first times the other two, plus the first times the derivative of the middle. The derivative of the middle will be negative 2/3 x minus 6 to the negative 5/3. Oh man, back inside 1 times the third, plus the first negative x to the negative 1/3 times the second times the derivative of the last one, which is just 1. I think this is good. Let me just double check. Zoom, zoom. Boom, boom. Boom. Boom, boom. And boom, boom, boom. Yeah. Okay, so now I have this just like, oh my god, horrible, terrible, negative fractional exponent giant mess. Let's try to make it pretty. So if we make it pretty, let's see. I can factor out a 1/3 from all three terms. So let's do that. I'm going to take out some number of x's. Well, I'm going to take out the lowest power, which is that one. So it's x to the negative 4/3. You should be practicing. You should have done this already by yourself. Don't just watch me do it. Okay, and I can also take out some x minus 6's because they all have x minus 6's. So I'll take out the lowest power of x minus 6, which is to the negative 5/3. Okay, so let's do it. Well, I took out the 1/3. I took out that. So I need an x minus 6 to the 1 times an x minus 4. Over here, the negatives cancel. I took out the 3, so that's going to be plus 2. And it's x to the negative 4/3, so I need an x here. And then that's gone, and then that's there. And then there's going to be a minus. Also, I took out a 1/3, so that I need to make that a 3. And then I took out x to the negative 4/3, so that's going to be an x. And then, is that it? Oh, and I took out an x minus 6 to the negative 5/3, so that's an x minus 6. Alright, so that's actually that was actually pretty hard, but the beautiful part of this method is that now we just have like a, in basically one difficult line of algebra, I've converted this all into like a nice little polynomial over here. So let's simplify this. This is like x squared minus 10x plus 24 plus 2x squared minus 8x minus 3x squared plus 18x. And I think my memory is that this turns out very beautiful. That canceled, that canceled, that canceled, that canceled. Yes. So you're left with just a 24. So the 24 cancels with the 3, and our second derivative then just turns out to be 8x to the negative 4/3 x minus 6 to the negative 5/3. Or, if you want to write it in nice notation, it is 8 over x to the 4/3 x minus 6 to the 5/3. Okay, so this is my first derivative, or I guess this is the best version right here. And this is my second derivative. That was a lot of work. If you mess up, then it's all wrong, and it's really easy to mess up. Because I messed up like 3 times while I was doing it on my first try 10 minutes ago. Anyway, there it is. So now that we have these derivatives, we can make the sign charts. So let's do that. I'm gonna move this slightly, so pause or whatever if you need to. Let's do a little bit of that. I think this is a good idea. Maybe like this. Yeah, sure. Hopefully that's visible. Yeah, let's do it like this. Okay, so let's make some sign charts for this. Let's first make a sign chart for f. That's kind of worth doing. So let's see when f is positive and when f is negative. Well, what is f? F is basically the cube root of x minus 6 over, or negative cube root x minus 6 over x to the 2/3. Okay, so you really need to know some stuff about math just to be able to analyze when that's positive and negative. So first of all, anything to the 2/3 is automatically positive, so that can be ignored. And the cube root of something positive is positive, the cube root of something negative is negative. So this is going to change sign at 6. There's going to be a sign change at 6, and because there's a negative in there, it's sort of like upside down line, so it's going to be positive, negative. Alright, that just tells me that this function's positive less than 6 and negative after 6. Okay, now let's look at the sign of the first derivative. Well, it's right here. And let's see. We get something is happening at 0, something's happening at 4, and something's happening at 6, it looks like. Okay. Again, cube root of something positive is positive, cube root of something negative is negative, so sign change at 0, also sign change at 4, but x minus 6 to the 2/3 will be always positive, because anything to the 2/3 is going to be positive, so there's not going to be a sign change at 6, so it's relatively sophisticated. So if there's no sign change at 6, then only 0 and 4 are relevant, and since there's also a negative, that makes it like negative quadratic-y, so end behavior down, so it's going to be negative, positive, negative, no sign change at 6. In other words, this function's decreasing, increasing, and then decreasing all the way after 4. Okay, let's look at the sign of the second derivative. The second derivative, well, something to the 4/3, positive is positive, and something, if it's something negative to the 4/3, the 4 will kill it, right? So therefore, again, no sign change at 0, but there will be a sign change at 6 because something negative to the 5/3 is negative, something positive to the 5/3 is positive. So there's going to only be one sign change, and that's at 6 only. If you want to put in 0 here, you can, but there's no sign change there. And the coefficient's positive, so it's just negative, positive. So this is concave down, concave down, concave up. Okay, so now we put it all together with our F number line. So we're going to have a spot at 0, a spot at 4, and a spot at 6. I probably should have noted that the domain of this function is all real numbers, because I can take the cube root of anything and I can, yeah. So that's good to know. Alright, so what's going on? On the interval from negative infinity to 0, this function is decreasing concave down. So decreasing concave down like that. From 0 to 4, it is increasing concave down. So it looks like that. From 4 to 6, it is decreasing concave down. So like that. And from 6 to infinity, it is decreasing concave up. So that picture gives me that, so that all this information was basically to determine all of this information here in this chart. Okay, this problem is really serious. Basically, if you can do this problem, you can do anything. All right, so let's jump in. Let's try to make a graph. Oh, I probably need some values. So what's f of 0? F of 0 is 0. F of 6 is also 0. So we need a value for f of 4, or at least an approximation. I have no idea what this is, but this is going to be negative 4 to the 2/3 times, and let's see, when I plug in 4 into the function, I get negative 2 to the 1/3. So times negative 2 to the 1/3. So whatever the hell that is, I really have no idea. Guess the negatives cancel. So, well, 4 squared is like 16. So this is like cube root of 32, I guess. Because it's 2 to the 4/3 times 2 to the 1/3 is 2 to the 5/3. Yeah, it's a cube root of 32. I really don't know what the cube root of 32 is, but I know the cube root of 27 is 3. So I'm going to say that this is like about 3.2 or something like that. All right, let's make a graph. So here we go. I know this function is 0 at 0. Just checking to make sure you can see everything. Yeah. 0, 0. At 6, it's also 0. And at 4, it's like 3.2 or something. Okay, what else do I know about this function? I know, I know something at 4. At 4, the derivative is positive and then negative. So that means there's a relative max at 4. I also know that the derivative is negative and then positive at 0. So there's a relative min at 0. So I'm going to do a little bit of this. And then I also know that I'm not sure what else I do know. What else do I know? There's a point of inflection at 0, etc., etc. Okay, let's try to graph this thing. Okay, well, on the interval from, and this gets really hard. Oh, by the way, you should definitely, there's like 5 things you have to be able to do correctly here. You have to correctly take the derivative. You have to correctly factor it. You have to correctly express it algebraically. You have to correctly take the second derivative. You have to correctly factor it. You have to correctly express it. Then you have to correctly analyze the sign charts for these things, and then you have to put it all together. And now you have to graph it. Okay, so at least this part you should definitely be able to do. This is the sort of calculus part. The rest of this is just kind of like a lot of algebra. So here comes now the thinking. What does this function look like? Please pause and try to graph it yourself. Okay, unpause. Well, this function is decreasing concave down until 0. That's kind of confusing to me, if it's because I know there's a relative min here. Also, the function's positive until 6. So if it's decreasing and concave down, it must kind of do like that or something. And then suddenly it goes from decreasing concave down to increasing concave down, which tells me that there must be like a sharp point here. And then we get to the relative max at 4. And then what happens at, oh, by the way, how else do I know there's a sharp point here? If you go back to the formula for the derivative, I'm sorry that I have to like rotate this camera a little bit. If you go back to the formula for the derivative, you can see that when x is 0, or when x is near 0, well, okay, when x is 0, the derivative is undefined. So, but when x is near 0, the derivative will be huge. And in fact, if you look at the sign chart, to the left of 0, the derivative is negative. To the right, it's positive. So, and then near 0, it's like it makes this thing gigantic, which tells me that on my graph, I'm going to have like a vertical tangent line at x equals 0. And there's also going to be a vertical tangent line at x equals 6, because if x is close to 6, that makes this denominator tiny, that makes this fraction huge. So my derivative is basically infinity at 0 and at 6, which means I have a vertical tangent there. So what is this doing at 6? Well, I'm following my chart. Now I start decreasing, but I'm still concave down. And then suddenly I have a vertical tangent. I have a vertical tangent here at x equals 6. And then my concavity changes from being concave down to concave up. So this, believe it or not, is basically what this function looks like. If you check it out, it matches all of the pieces that we found. You have relative max here at 4 comma cube root 32. This is a point of inflection because it's where the concavity changes. This is also a point of inflection, I guess, because the concavity. Oh, actually, no. This is not a point of inflection because the concavity doesn't change there. That's just a place where the derivative does not exist here. The derivative also does not exist at 6 for kind of a different reason. Yeah, there's only one point of inflection when the concavity changes, when the second derivative changes sign from negative to positive. That's pretty much it. I feel like there was one more thing I had to say. Oh yeah, two more things I have to say. One is, you kind of, if you were pretty smart, you kind of could have predicted this whole thing all along. Because if you go back to the original function, if you just sort of know some pre-calc and you're willing to make some good guesses, this basically is kind of like a function which locally near 0, this is out of the window. Let me rewrite the function. The function to rewrite the original is negative x to the 2/3, x minus 6 to the 1/3. So if you think about what that's saying, it's saying that my function should locally look like x to the 2/3. And that's what x to the 2/3 looks like locally. It's like the bird. And also locally, it should look like the cube root of x minus 6. And that's kind of what a cube root function looks like, shifted over 6. So if you combine kind of like a cube root function and a x to the 2/3 bird function, and you flip it like upside down, then this is exactly the graph. So all of that stuff should kind of make sense. Okay, there's like one more thing, but whatever, I think that's good. All right, if you can do this problem, you can do anything. Algebra, calculus, and curve sketching. So this is a sort of advanced curve sketching lesson. So good job. I will see you guys next week.